Welcome back to the deep dive. We are back with another stack of research, and honestly, today feels a bit like we're finally taking the training wheels off. We are looking at a serious upgrade to how we think about thinking.
It is a massive upgrade.
Yeah,
If our last discussion was, say, learning the alphabet, today is writing a novel.
I love that. In our last deep dive, we spent a lot of time on propositional logic. And to be honest, after reading the source material for today, it feels a bit blocky.
Blocky is a good word for it.
Like trying to paint a detailed portrait using only massive square pixels.
That is a great analogy. The source text actually calls propositional logic puny.
Puny. I felt bad for it.
It is harsh, but, well, it's fair. Because propositional logic treats the world as just a bunch of disconnected facts. It is raining, true or false. The car is red, true or false. But it can't look inside the facts. It doesn't get that a car is an object you can paint or drive or sell. It just sees a list of isolated switches.
And the real world isn't just a switchboard. It's messy. It's full of things. And those things have complex relationships with each other. A car belongs to a person. A person has a mother. The mother has a house. Propositional logic just chokes on that.
Which is why we need the upgrade.
Right. So today we are introducing the solution, first-order logic.
Or just FOL, yeah. That's what you'll usually hear in the trade. This is the mathematical framework that lets us describe a world that's blessed with objects, relations, and functions. It's really the bedrock of how we try to teach a computer to have common sense.
And our mission today is to decode that framework. We're going to look at how the language we speak, whether it's English, Spanish, or C++, actually rewires our brains. We're going to walk through the logic traps that crash AI systems, and some of these are genuinely tricky.
Oh, they are. Very easy to fall into.
And we are going to find out why a computer couldn't figure out a simple circuit board because nobody told it that the number 1 is different from the number 0.
That is a classic debugging horror story.
Yeah.
One of my favorites.
So let's start with the big picture, language itself. The source material opens by comparing programming languages to natural languages, and they are almost opposites, aren't they?
Completely. Think about the code running on your laptop right now. C++, Java, Python. These are what we call procedural languages. They describe a process.
Do this, then do that. If X happens, execute Y.
Exactly. They are precise, they're mathematically perfect, but as the text points out, they don't really know anything.
Right, they aren't reasoning. C++ doesn't sit there and ponder the universe. It can't derive new facts from old ones unless you explicitly code the path. It's an obedient worker, but it has zero imagination.
Whereas natural language, English, Spanish, Mandarin is the Wild West. It's incredibly expressive. You can describe a sunset, a feeling, a logical paradox, a dream. But the cost of that expressiveness is ambiguity.
The source quotes Steven Pinker on this. If I just say the word spring, what am I even talking about?
Exactly. Are you talking about the season after winter, a metal coil in a mattress, a leap into the air, or sorts of water?
Context usually saves us humans. If I say, I broke a spring in my mattress, you know I'm not talking about the season.
But a machine gets stuck.
Yeah.
It doesn't have that lifetime of context to draw on.
And this brings us to a fascinating sort of intersection called the Sapir-Whorf hypothesis. This is the idea that the language you use doesn't just describe your thoughts, it actively shapes them. It puts guardrails on your reality.
It's a controversial idea, for sure, in linguistics. But there is some compelling data in the text to back it up. My favorite example is the Gugu Yimithirr people in Australia.
I was reading that section twice to make sure I got it. This is the direction example, right?
Yes. In English, we use relative directions. Front, back, left, right.
Yeah.
Those are egocentric. They depend on which way you're facing.
Okay.
But the Gugu Yimithirr language lacks those words entirely.
Which sounds impossible. If I'm sitting at dinner with you and I want the salt shaker that is near my left hand, how do I ask for it?
You can't say left. You would have to say, please pass the salt to the west. Or maybe there is an ant on your southeast arm.
So to even speak this language, you have to know where north is at every single second of your life.
Exactly. And because the language demands it, their brains have adapted. They have this phenomenal internal compass. They can navigate open terrain better than almost any English speaker, simply because their software, their language, requires absolute positioning.
That is wild. It's like their brain is running a background GPS process constantly just to handle basic grammar.
And it applies to things we think of as totally arbitrary, like gender. The source details the Boroditsky study from 2003.
The bridge study. This was fascinating.
So English doesn't really gender inanimate objects. A bridge is an it. But in Spanish, bridge, el puente, is grammatically masculine. In German, Die Brücke is feminine.
And the study found that this grammar actually trickled down into their perception of the object.
It did. They showed speakers of both languages a picture of a bridge. The Spanish speakers, who see the word as masculine, use adjectives like big, dangerous, strong, and towering.
Huh. Stereotypically masculine traits.
Right. But the German speakers, looking at the exact same photo, described it as beautiful, elegant, fragile, slender.
That is the power of representation. You force the mind into a category, and essentially that is what first-order logic is trying to do for AI. It's a compromise. We want the precision of computer code so we don't get confused about Spring, but we want the descriptive power of human language.
We want to talk about objects and relations.
So let's build this world. The source talks about ontological commitment, which sounds like a marriage vow, but I gather it just means, what do we assume exists in our universe?
Correct. If you are writing in first-order logic, you are committing to a universe made of 3 specific building blocks: objects, relations, and functions.
Okay, let's use the example from the text because it's oddly specific. We have Richard the Lionheart and his brother, King John.
A classic historical rivalry. So first we have objects. These are the nouns. Richard is an object. John is an object. The crown is an object.
And interestingly, the text points out that even their body parts, like Richard's left leg, are also objects.
In this logic, yes. Anything you can point to and name is an object.
Then we have relations. These are the connections between objects.
Think of these as adjectives or verbs that connect things. Brother is a relation holding between Richard and John. On head is a relation that holds between the crown and King John. Relations just return a simple yes or no. Are they brothers? Yes. Is the crown on the head? Yes.
And then we have the tricky one, functions. I feel like this is where people get tripped up.
It is the most common point of confusion. In Python or Java, a function does something. It calculates a value, it runs a script. In logic, a function is just a way of pointing.
It's a reference.
Exactly. Take left leg John. That isn't a command to go cut off his leg. It's just a way to identify an object based on its relationship to another object. It's saying the thing that corresponds to the left leg of John.
And the key rule, if I understand this right, is that a function has to point to exactly one thing.
That is the rule. Father of John is a valid function because he has only one biological father. But brother of John is not a function.
Because he could have many brothers, or none.
Right, so brother remains a relation. You can be a brother to many people. But a function is a one-to-one mapping. It's a way of naming something without knowing its name. I don't need to know the name of John's left leg to talk about it. I can just use the function left leg John.
Okay, so we have our nouns, objects, our connections, relations, and our pointers, functions. Now we need to scale this up, because if I want to say all kings are tyrants, I don't want to list every single king in history individually. That's inefficient. I need a shortcut.
And we call these shortcuts quantifiers. They let us handle groups of objects. There are 2 big ones you need to master. The first is the universal quantifier, written as an upside-down A. It means for all.
For all x.
Let's try to translate all kings are persons. In logic, we would write, for all x, if x is a king, then x is a person.
Okay, now the source warns about a very specific bug that happens here. It says people mess up the connecting logic. They use and instead of if-then.
This is the universal trap. It's so easy to do. Suppose you wrote, for all x, s is a king, and dx is a person.
To me, in casual English, that sounds okay. Everything is a king and a person.
But think about what for all x really includes. It includes everything in the universe. The crown, the left leg, the sandwich you had for lunch. If you use and d, you are asserting that your sandwich is a king and a person.
I see. You've accidentally turned the whole universe into royalty.
Precisely. You're saying being a king and being a person is a universal property of existence. You don't want to say that. You want to say, if it happens to be a king, then it is a person.
So the rule is, with for all, you use implication.
Correct. Now let's look at the other tool, the existential quantifier. The backwards E. This means there exists, or there is at least one.
Like King John has a crown on his head.
Right. In logic, we say, there exists an x, such that x is a crown and dx is on John's head.
And I'm guessing the trap here is using if-then instead of nd.
You are spot on. If you said there exists an x such that if x is a crown, then it is on John's head, you break the logic completely.
Walk me through why that breaks down.
Because of how implication works logically. An implication is technically true if the premise is false. It's a weird quirk of math. So if I pick Richard the Lionheart, Is Richard a crown?
No.
So the IF part is false. And in logic, a false start makes the whole implication statement true by default.
Yeah.
So you could satisfy the rule, John has a crown on his head, by simply pointing to Richard and saying, well, Richard isn't a crown, so the rule isn't broken.
That lets the computer cheat. It can say, yes, John has a crown just because Richard exists.
Exactly. It satisfies the condition with a non-crown object. It's useless. So the rule of thumb, if you want to say something exists, you have to be specific. It is a crown, and it is on his head. No ifs allowed.
Universal uses implication. Existential uses and. It feels like learning grammar rules for a new language.
That is exactly what it is. It's the grammar of reasoning.
Let's look at what we can actually do with this grammar. The source gives us 3 worlds to test this logic on: family trees, the Wumpus game, and electronic circuits.
The family tree, or kinship domain, is great for understanding the difference between what we tell the computer and what it figures out for itself. This is the difference between axioms and theorems.
An axiom is a starter rule, right? A definition.
Yes, a definition we provide. A mother is a female parent. The computer can't guess that. We have to tell it. That's an axiom.
But a theorem is something it figures out on its own from that.
Yes. So if we define sibling correctly as sharing a parent, the computer can then prove a theorem. Siblinghood is symmetric. If I'm your sibling, you must be mine. We didn't write a rule for that specific fact. The logic discovered it based on the axioms.
It's derived knowledge. That's the common sense kicking in. Now remember the Wumpus World, that video game grid with the monster and the pits we talked about last time?
Hard to forget that one.
In propositional logic, the breeze, the clue that a pit is nearby, was a nightmare to code. To say pits cause breezes, we had to write a rule for square 1, then a different rule for square 2, then square 3.
It was so bulky,
Yeah.
inefficient. But with first-order logic, we have variables. We can just say, for all squares as, if as is breezy, then there is a pit in a neighbor of as. Boom.
One sentence covers the whole board.
One sentence. And it doesn't matter if the board is 10 squares wide or 10 million squares wide. The logic holds. That is the expressive power of that little variable.
That is infinite scalability. But my favorite example from the text, and maybe the funniest, is the electronic circuit. They were trying to verify a 1-bit adder, a simple digital chip.
This is a famous case in knowledge engineering. It really illustrates how literal computers are.
So the engineers describe the gates, the wires, the connections. They load it all into the logic engine. And they ask, does this circuit work? And the computer says, I don't know.
They spent hours debugging. The logic looked perfect. The definitions of the A and D gates, the OR gates, everything was perfect. The wiring was perfect. But the system couldn't prove the output was correct.
And what was the missing piece?
They had forgotten to tell the computer that 1 is not 0.
No, it sounds so silly to us. Obviously 1 is not 0.
But to the logic engine, 1 and 0 are just random symbols. They could be synonyms for the same object, like Richard and the Lionheart. Unless you explicitly write an axiom that says 1 is not equal to 0, the computer has to consider the possibility that they are the same thing.
And if 1 is 0, the circuit creates a short and the logic fails. It's like the Richard's left leg issue again. The computer has no outside context. It only knows what you tell it.
And this leads to a really practical problem for anyone building, say, databases or commercial AI. We call it the unknown brother problem, or the open versus closed world.
Explain that.
In pure logic, if I tell you Richard has 2 brothers, John and Jeffrey, and then I stop talking, you don't actually know if he has only 2 brothers.
Right. Maybe there's a secret brother, Steve, hiding in the attic. Logic leaves that door open.
It does. It assumes an open world, that there might be facts out there we just haven't discovered yet.
Which is technically true in the real world. But if I'm running an airline database, I can't operate like that. I can't say, well, there's no flight listed to New York at 5 p.m., but maybe there's a secret flight I don't know about, so I can't tell you no.
Exactly. You'd never be able to answer a customer's question.
Yeah.
So databases use a shortcut. It's called the closed world assumption.
Which basically means if it isn't in the database, it doesn't exist.
Right. It forces the system to treat the absence of information as a false. If the flight isn't listed, there is no flight. If a brother isn't listed, Richard has no other brothers.
It's seek code.
It is. It violates pure logic, because technically we don't know for sure. But it makes the system actually useful for business. It lets us complete the picture.
So we've gone from the puny boxes of propositional logic to this rich, interconnected world of first-order logic. We've seen how language shapes thought, how we define objects, and how we have to be incredibly careful with our for-alls and their exists.
It's a powerful toolkit.
Yeah.
But before we wrap up, I want to circle back to that bridge example one last time.
The German versus Spanish bridge.
Yes. Think about what we are doing with first-order logic. We are teaching our AI models to view the world through this very specific lens. We're forcing them to slice reality into objects and relations.
Because that's how we, or at least those of us speaking Indo-European languages, tend to see the world.
Exactly. But is it the only way? The source hinted that while logic treats A or B consistently, our brains process things differently based on context. By forcing AI into this rigid object relation structure, are we giving it common sense? Or are we just infecting it with our own limitations?
That is a heavy question. Maybe there's a way to understand a bridge without breaking it down into slender or strong objects. Maybe there's a Gugu Yumithir version of AI code that we haven't even invented yet.
Maybe.
Yeah.
But for now, if you're coding that AI, you better make sure you teach it that the bridge is an object and that 1 is definitely not 0.
That is non-negotiable.
Otherwise, you're going to have a very confused circuit.
Something to think about the next time you look at the world. Are you seeing the truth or just the objects your language lets you see? Thanks for listening to The Deep Dive. See you next time.